So I think in last lecture we did some question of Coulomb's law, and today what I said was that we'll start the vector form of Coulomb's law, right?
Yes, sir.
So far, have you understood the concept of electrostatics, or finding it's really difficult or easy? How you find
Sir, I'm able to understand, sir.
it? Okay. And are you able to understand in your school, like what they are teaching?
Yes, sir.
Very good. So today we are going to study something called vector form of Coulomb. So let's say we have two charges at two separate locations, and for the sake of convenience, we are going to assume both as positively charged particles. One with magnitude q1 and other with magnitude q2. So q1, q2 represents the magnitude of charges. Based on the situation, we may consider q1, q2 with sign as well. So let's say this is the charges. Now, because both are positive charge particles, so will they attract or repel? What they will do?
So they'll repel each other, sir.
Right. So the force experienced by charge particle 1 will be towards this direction, right?
Yes, sir.
Whereas the force experienced by the Q2 will be in this direction, right?
Yes, sir.
So can I call this as force acting on the first particle applied by the second particle? So this is a double subscript notation, and this is how we understand the meaning of it. So when I write F12, it is not 12, rather it's a force on 1 due to 2. So the first letter is the one which is experiencing the force, and second letter is the one which is applying the force. So similarly, we can say this is force on 2 due to 1, right?
Yes, sir.
Now I want to express this into vector form, and what is given to us is their respective position vector. So this is the position vector of the first particle with respect to origin, and this is the position vector of the second particle with respect to the same origin. So let's say the first particle is located at a position vector r1, and second is located at a position vector r2. So what we can understand that this is r1, this is r2 is the location of the particles. But to write the Coulomb's law, what we need is the separation between them. So r1, r2 really doesn't matter. What matter is what is their separation, because the separation will decide the force value, right?
Yes, sir.
So now if I ask Q1, where is Q2? So Q1 will point, maybe it's fingered like this. But if you ask Q2, where is Q1? This will point like this. So this is called position vector of 2 with respect to 1, or as seen by 1. And this arrow we can write as position vector of 1 with respect to 2. Do you realize this?
Yes, sir.
So we can put into some okay, like a nomenclature. So R21 is PV of 2 with respect to 1. And R12 is equals to PV of 1 with respect to 2. Okay. So what we can also see that force on 1 due to 2 and R2, R12, these two are parallel. You can see this and this, these two vectors are in parallel, right?
Yes, sir.
And similarly, these and these vectors are in parallel. So from the concept of vector, okay, first let me add the name. This is the force on one due to two, right?
Yes, sir.
And this is also force on two due to one. Okay. So what we can realize that the vector F12 is parallel with vector R12, right?
Yes,
So
sir.
now from the concept of vector, we know that if two vectors are parallel, it means their unit vectors must be equal.
Yes, sir.
Because the vectors cannot be equal because they are representing different physical quantities, so they cannot be equal. One is force, other is displacement or position. So we can only equate things which are equal dimensionally as well. And unit vector is such a vector which is always dimensionless, and that's why we can equate it. Okay, if the magnitude is equal. So what we can say that since F12 is parallel to R12, so their unit vectors must have same direction, isn't it?
Yes, sir.
And because they are unit vectors, so they are equal in value also. So this property is, I mean, something which will help us in writing the answer. So from here you can see clearly that the formula for force on 1 due to 2, you can write the magnitude and multiply with the unit vector of the second vector, right?
Yes, sir.
There are many ways of writing this F12 E R12 vector, or simply connect them because the magnitude of force is same for F. We also know that mod of F12 is same as mod of F21 because these are action reaction forces, so we can just call it F. So this is easy to write like this. So this is how we can represent the vector form of force. We can say F12 is simply the modulus into E vector of R12 or F21. Now this is easy to write. Is F into E vector of R21. So that's a small change you can do here. You will get the answer. Is this clear?
Yes, sir.
Okay. Let's stop. So this is how we can add the force value. So we'll see some example. Now this kind of vector form is not much use, but still we should know. So
Okay, sir.
if I expand the formula, because see the F12 is mod of F12 E vector of R12. So the question is how to write the force formula. So force will follow the Coulomb's law because that's a simple value. K Q1 Q2 by R square. And what is the separation? R12 mod whole square, right? In vector
Yes, sir.
form. And R12 itself is R12 upon mod of R12. So you can see clearly that the vector notation is Q1 Q2 upon mod of R12 whole cube R1. Okay.
Yes, sir.
So F12, and we can further expand it. From triangle law, we know that R12 we can attach R1 minus R2.
Yes, sir.
whole cube, and this we can again attach R1 minus R2. So you can see the denominator is a number, but the numerator is a vector. So this part is only vector, right? Everything the rest is number. This is the number.
Yes, sir.
Now there is small catch in vector representation of the formula, and the catch is while deriving this formula, I presume that Q1, Q2 are having same sign; they are positive. But what if that's means the sign of Q1, Q2 are opposite? So if Q1 is positive, Q2 is negative, then the force will reverse the direction, right?
Yes, sir.
Because if they are opposite sign, it means they will attract instead of repulsion.
Yes, sir.
So the question is how we can accommodate that flip in the direction using the same formula. Like what we should do so that the flipping part is also taken care by the same formula. We need to write the separate formula. And the answer is very simple. While you write this formula, make sure that you write the charge with sign. So in this particular formula, just in order to accommodate both the scenario, we put Q with sign also. So here in formula, substitute Q1 and Q2 with its sign. So now it will take care of everything. So let's say if you put a Q1 as negative and Q2 as negative, so both are having similar charge. It means both will repel, right?
Yes, sir.
And minus into minus is plus, so that will also take care of. Now if I make it both positive, then again positive. But if I choose one charge as positive, other as negative, then definitely it will give you negative sign, and the negative sign will flip the direction. Understood?
Yes, sir.
By simple modification, we can take care of the sign. I mean the nature of charge also. So the formula is simple. You just start with the formula. So what you need to write is K Q Q2 by mod of our whole cube. So you can also write like this: F12 is K Q1 Q2 upon separation whole cube, because see we are putting one R vector here also. So because you can see dimensionally this is extra, so this will also get extra power here. Because eventually the dimension should be K Q Q2 by R square, right?
Yes, sir.
Just in case you're getting confused, you can remember this way. Okay, the denominator should be RQ because the numerator is having extra R. So similarly, F21 you can write as, or you can just switch it like K Q2 Q1 upon RQ. So you can say that the force between any particle I and J is KQI QJ upon RI minus RJ mod of whole cube Ri minus Rj, and this is our final formula. So you can write for any two particles in this format. Okay, so it's very easy to remember because you see there's a sequence Ij, 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 Ij everywhere Ij. Okay,
Yes, sir.
so let's solve one problem, then we'll see more application of it today. So uh, so we have a charge that's a -2 microcoulomb, and we have +6 microcoulomb. There are two charges. So okay, I can represent as minus and plus. Now, what is given to us that the coordinate, like the location of the negative charge is 2 comma 1 comma 0, and the location of positive charge is minus 1 comma minus 1 comma 1. So let's say this is the location of these two charges. The question is, if I call the negative charge as the first charge and this is second charge, so what is the force on 1 due to 2? So how to write it? It's very simple. K Q1 Q2 upon R1 minus R2 modulus cube R1 minus R2 without modulus, right?
Yes.
So let's substitute the value and then it's done. So 9 into 10 to the power 9. Then what I said is, while using the vector formula, this particular formula, we put charge with sign. So minus 2 micro, because micro is a number, so it's 10 power minus 6. Q2 is 6 micro. Okay, we don't write Coulomb.
Yes.
It's only. Now the look at this, how to write this. R1 minus R2. So this is R1. This is R2. Now let's separate. 2 minus minus 1. How much? 3. 1 minus minus 1. 2. 0 minus 1. See, it's very easy to write. And once you write the denominator, you can just write it the same thing here. 3 I care. This is how we write. Understand?
Yes.
And therefore, okay, let me simplify what I can. So it's 12 into 9, 108, right? Minus 108. So I'll make it 108. Okay. And macro is minus 12 and 10 power 9 is okay, 9. So it's minus 3, right?
Yes.
Now mod of this is interesting. So 3 square plus 2 square plus 1 square, 9 plus 4 plus 1 is 14. So root 14 whole cube. What is the cube of root 14? So mod of the number is root 14 and then we have whole cube. And then we have 3 I cap plus 2 j cap minus k cap. And we can further simplify it 108 10 power minus 3. And what we can write here is 14 root 14. That's the meaning of cube, right?
Yes.
Now I have removed the minus sign because here we should write the number only. All negative sign, all sign should be within the vector notation. So we can write as minus 3 I cap minus 2 j cap plus k cap. This minus I have taken inside. So now you can see this is the number and these are the coefficients in different direction. Okay.
Yes, sir.
So you can use calculator to simplify this value. But anyway, I'm leaving this part. So not an issue. 108. Let me just divide by what this is 0.00206 minus 3 minus 2. Okay. So okay, let c equals to 0.00206 just to write easily. So what is the x component of the force? You can see the x component is minus 3c.
Yes, sir.
What is y component force? It's minus 2c. And what is the z component force?
1C.
Is c. Yeah, 1c. Very good. So this is how we write the vector notation. So to write the vector from a force, you need to convert charge particles and you have to write the location. So you have to use a coordinate system to apply the same. So let me give you some better example in which you can apply. Although it is not required to solve that way, but just for practice and understand this concept, the very concept we will be doing this problem. So imagine I take a equilateral triangle and it is located like this, and the side length of this triangle is A. This is the origin, you can see. Now at the vertex of this triangle we can put some charge. So let's say this is positive charge, this is also positive, this is also positive. Let's keep it a simple question. All charges are equal. But even though it's I mean, different charge, you can apply it. So that's not an issue. So for the sake of writing, we can call it charge number 1 and charge number 2 and charge number 3. So the question is, what is the force experienced by the first charge part? And the answer is simple. The first will experience force due to 2 as well as due to 3, right?
Yes, sir.
So who will apply force on 1? So 2 and 3 will apply. That's simple. Similarly, force on 2 will be applied by 3 and 1, and force on 3 will be applied by 3 1 and 3 2, right?
Yes, sir.
So you can solve any of them. So we know the way of writing the formula in notation. So you need to first write the coordinate. So the coordinate of the first particle will be 0 0. So you can write as r1 equals to 0 I cap plus 0 j cap. Just put the writing. So what is r2 then?
Sir, R2 is A by 2, comma, A by 2 I cap and 3 root 3 by 2 A J cap.
Very good. And what is r3?
A I cap plus 0 J cap.
Very good. So you know all the position vectors, so it's very easy to write. So now it's only about expanding the formula. So the F1 is F12, so we can write as K Q1 Q2 by R1 minus R2 whole cube into R1 minus R2, right?
Yes,
The
sir.
first expansion. The second expansion will be K13 1 3. So this is 1 3 whole cube and 1 minus 3. So it's very easy to just keep on substituting the value. And although it looks lengthy, but it's pretty easy because we need not to do any calculation because we know the separation is A, right? So I can better I
Yes,
can
sir.
write as Q1 Q2 by just A cube, right?
Yes, sir.
So only this part we have, and also Q is also equal. So that's pretty easy. The question, so KQ square by A cube is the term which we have common from both because this is same and this is same, right?
Yes, sir.
So what we left with is 1 minus 2 plus 1 minus 3. So 1 minus 2 plus 1 minus 3. And it's good to simplify this first. So we have 2R1 minus R2. Oh, luckily R1 is 0. So this entire term is 0. So we are getting Q square by A cube. And what is minus R2 and minus R3? So if you take, okay, take minus common. then it is R2 plus R3. So if you add these two, what we'll get is 3 by 2 I cap and root 3 by 2 A j cap, right?
Yes, sir.
So now this is representing that both terms are negative. The I coefficient is negative because, okay, you can make it plus, you can make it minus here. So this is what you can also do. What you can see, the I coefficient is negative and J is also negative. So which quadrant?
Sir, the third quadrant.
Right. So if I want to know the angle, so you can just find the tan theta, just a value. So this is the Y coefficient upon X coefficient, which is root 3a by 2 upon 3a by 2, which will become 1 by root 3, right?
Yes, sir.
And this implies that theta is 30 degree. So the direction of force we can actually find in this particular case because of the nice values. And what we can realize that the net force acting on the first charge particle will be at 30 degree, but in the third quadrant, right?
Yes, sir.
So this is the force acting on one, and this is 30 degree in the third quadrant. So this is how we can interpret or use the vector notation to solve the question. Now, sometime in board examination, they may ask you that use the vector method to solve this problem. So you are supposed to solve like this. Okay.
Okay, sir.
But we'll now see that how we can solve this question without doing all this calculation. Almost mentally, yeah. This is easy question.
Yes, sir.
So what we saw was the unnecessary lengthy method, but that is not required. So if I am only supposed to find the magnitude of force, Q and the side length is A, so let's say we would like to know the force acting on this charge. Okay. So you will ask this yellow charge that what other charges are doing on it. Okay. So let's call it 1. So ask 1, what 2 is doing? What he will say? Push or pull?
Sir, so push, sir.
Push. So in which direction? 1 will experience push in which direction?
Negative x-axis.
Very good. So we always ask the one who experiences it, not the one who applies it, right?
Yes, sir.
And there's a very simple analogy you can remember, like when small kids fight, they fight with each other and they will, what do they do? They start crying and they go to their mama. And the very next question mama asks that, who has bitten, right? This is the
Yes,
question.
sir.
Mama never asks that, whom you have bitten, right?
Yes, sir.
Now this is the biasness, like every mother will have with their kids. Same biasness will keep here also because this is going to be useful to us. So we always ask the one who experiences it. Like you ask 1, what 2 has done to you? What 3 has done to you? We never ask that what you have done to 2 and 3. That's the simple rule of biasness. So
Yes, sir.
I was unfortunate. My dad used to ask what you have done. Okay, knowing my nature, it was relevant. So anyway, So now the 1 will experience in the left side, but what about the 3? 3 will push like this.
Yes, sir.
Now, because of symmetricity of distance and the magnitude of charge, can we say the force, the push must be equal in value at least?
Yes, sir.
If this push is F value, then this must be also F, right?
Yes, sir.
Now, because these are two vectors of equal value, so the resultant of the two will be exactly in between, isn't it?
Yes, sir.
So this is called the line of symmetricity. This is called the direction of net force, but it's also the, if you look carefully, this is the line of symmetricity. So there's a concept of symmetricity, which is very, very powerful in solving questions. So if you can see the line of symmetricity, so this is the force line of symmetricity. So the net force is acting this way. So what we are supposed to do is we are supposed to simply take the component of force along the line of symmetricity of the charge distribution, because that is going to be the direction of force also, right? So
Yes, sir.
the net force is pretty much simple, because we know this angle is 60 degrees, so this must be 30 and 30. So this is also 30-degree angle, correct?
Yes, sir.
So the rule is we resolve all forces along the line of symmetricity and we just add them. That's the answer. So what we can say, this is F cos 30 and F cos 30. So we can add 2 times. Okay. So the net force is how much? Root 3F, right? It is clear.
Yes, sir.
And we know F is the force between any two charges, which is KQ square by A square. And that's the answer. Understand?
Yes, sir.
The other way of solving this could be like this. So you may say, is this the only way to solve? The answer is no. There are many ways you can solve the way you like. So let me solve the method 3, because this is the one we have seen here. You really learn. You can imagine the complexity of this method and this method.
Yes,
So
sir.
now, because we have two forces, and let's say we are not interested in the line of symmetricity, that we should not be. We must be interested in the line of symmetricity. Because the moment you understand the line of simplicity, we can solve question almost mentally. So method 3 says that, okay, once you designate the forces, again write in vector form. So we can write as net force vector form is equals to how much? F minus I cap plus, like this is minus I cap. The other force we need to resolve along the x and y axis, we can write as F cos 60 minus I cap plus F sin 60 minus j cap, isn't it?
Yes, sir.
And you can clearly see that this we can rewrite as minus 3f by 2 I cap and root 3f by 2 minus j cap, and that is exactly the answer we got in the very beginning. 3 I cap by 2 minus root 3 j cap by 2. So f, now what is f? F is kq square by a square. And you can see, because I have taken a common, so even if you look at this point, you can take a common here, and this will cancel out the, this will become 2, right?
Yes, sir.
This is as good as writing kq square by a square into minus 3 by 2 I cap minus root 3 by 2 j. And exactly same thing we have got here, minus 3 I cap minus root 3 by 2 j. So there are various ways to solve the question. And in this particular case, we are lucky enough to apply the method 4 also. And why 4? Because we have two vectors and we know how to find the resultant two vectors. We have formula for that.
Yes.
A square plus B square plus 2AB cos 60 degree, right?
Yes, sir.
And see exactly 3F because cos 60 is half. So this is 3F square. You can write like this.
Yes, sir.
So that's pretty easy, right? So eventually can attest. So if it is finding the magnitude, then I think this is the best approach. But we'll try to restrict ourselves to the, I mean, two methods. The method 3 because 3 is very powerful. Why? Because no matter whether we have line of simplicity or not, this method is going to give you the answer. Eventually, everything you can attach in terms of I cap and J cap. So the method 3 is like resolve all vectors and get the answer. Just add it, right? So even if it is number of 4, so I increase to 3, 4, 5, 6, or any number, this is going to be help. Okay.
Yes, sir.
Okay. All right. So in JE problem, the symmetricity is important. So if you do not know symmetricity, you will be struggling long time or wasting a lot of time in solving simple question. So let's say if I give you problem of a square, so we have a square of side length A, and we have a charged particle at the vertex. For the simplicity, we are keeping symmetricity maintained. So we are doing symmetrical problem. So all charges are Q in value. So the question is find net force on any charge. Because it's symmetrical, so finding force on any charge will be same answer, right?
Yes.
So you try this out, then I'll solve. Okay.
Okay, sir. Sir, sir,
Yes, yes, tell me.
sir, is it root 2f plus f by 2, sir? I mean, f being kq square by a square.
Hmm. So you can draw the line of symmetricity, right? Symmetricity will be
Yes,
like
sir.
this. Assuming I'm
Yes, sir.
choosing that charge like this. Hmm. This is the force diagram, right?
Yes, sir.
So if I call this force as F, this is also F,
Yes, sir.
or let's say F1. But this force is F2 because this is having different separation.
Yes, sir.
But F2 is the line of, I mean, line of
The diagonal.
symmetricity. Yeah.
Yes, sir.
So the net force we can attach simply F2 plus root 2 F1.
Yes, sir.
And then it's only about substituting the values. So F2 is how much? AQ
F
square by?
root 2a whole square.
Yeah, correct. And F1 is KQ square by A square, right?
Yes, sir.
So we can take KQ square by A square common, and what we get is 1 by 2 plus root.
Yes, sir.
Very. So this is the right answer. So now you can do it for the other shape. Let's say if I give you a hexagon, and this is a really interesting question. Assuming it's a a regular hexagon, and if all charges are positive, we may flip the charges. I mean, still I can maintain the symmetricity by flipping alternate plus and minus. So this is what we can do also. So let's say alternate charges are plus and minus. Now, as long as it is alternatively, the symmetricity will be maintained. Let's say the
Yes.
side length is A and every charge is Q. So value wise, all charges Q. So plus Q minus Q plus Q minus Q. So you can, and it's the same question. Find the net force on any one charge. Okay.
Okay, sir.
So try this out. Then I will.
Yes. Sir, is the
Hmm.
alternate charges are negative, sir?
Yeah, yeah. Alternate charges are negative.
Okay, sir.
Done?
Sir, just a second.
Yeah. So what you're supposed to do is just draw the vectors and then take the line of symmetricity and take component and add it. Okay.
Yes.
So you may need to subtract also. All will not be in the same direction. So some is on the right, some is on the left. So you just take one as positive, other as negative. That's not an issue.
Okay, sir. So,
Yes.
sir, I'm getting 5f by 4 minus f by root 3 in the horizontal direction, positive
Okay.
x-axis direction. Sir.
So let me draw it first. Okay. So I think the line of symmetricity is this one, right?
Yes, sir.
So this, let's say, okay, I'll take this charge, okay, for the analysis part. So this charge will experience forces from the all other charges. So the one force is attraction in this direction, right?
Yes, sir.
But okay, this will also attract, and this is also attracting, right?
Yes, sir.
But the other rest of the two will repel. So this will repel,
Yes, sir.
and this will repel. So because we have three sets of distances, so we can name it in different. So if I call this as F1, this is also F1. So if I call this as F2, this is also F2, and this is alone F3, correct? So the net force will be how much? Take a right as positive, so you can see it's 2F1 cos 60
Yes, sir.
plus F3 minus 2F2 cos 30, because this is 30-degree angle, right?
Yes, sir.
Now the question is for F1, the answer will be KQ square by A square, value wise, because we are adding value. Direction we have taken care of, so we'll not put the direction, I mean sign, we just add the value. What about the F2? Because that's interesting.
Sir, f2 is, sir, I'm getting root 3a as the distance
Very
when
good,
I
that's
draw
correct.
a perpendicular.
Yeah, that's correct. So you can directly get the answer without doing all those calculations. This is 30-degree actually.
Yes, sir.
And this is A. So this is 2A cos 30.
Yes, sir.
Yeah, so that's correct. So F3 also, I mean F2 got is correct. And what about the F3?
Sir, f3 I'm getting as 2a, sir.
Very good. So it's 4A square, right?
Yes, sir.
And if you substitute what, so I think what you got the answer is correct. So that's very good. It's the right answer. So
Okay, sir.
after solving this two-dimensional problem, we can foray into one tough problem, which is three-dimensional problem. And maybe this is the first time we are going to the three-dimensional problem. So okay, so you can think for a while, and then I'll help you. So that's not a easy one. So this is the cube problem. So cube problems are very famous in every chapter of physics. Every now and then you will encounter the cube problem. So let's say we have a cube of side length A, and all charges are, let's say, positive. and we are supposed to find net force acting on any of the charges, because all charges are same, so finding force on any one will be same answer. So again here we also have the line of symmetricity, which will be the body diagonal, which you can also identify. And once you identify the line of symmetricity, the whole idea is to develop the strategy to get the component along that line. So you can think
Okay.
for a while, and then okay, I'll help you out.
Yes.
Just you think, okay, it's not about I'm expecting you will solve, but anyway, if you think it's good enough.
Okay. So,
Yeah, tell me.
considering the point that you had marked, sir, I'm getting the
Yeah.
answer as minus 7 by 3 f into I cap plus j cap plus k cap.
No, not like that. So you have taken the vector notation.
Sir, yes, sir.
So you must have written the coordinate of every charge particle. So we have in total 7 particles, right? And all are having different coordinates. So you have to use the, if you have taken the, says, let's say, x-axis, y-axis, z-axis. So this is 3-dimensional problem, right? The coordinate will be 3 values, 0, 0, 0.
Sir,
Will be,
1 second, sir.
yeah, a 0, 0. And you can do like this.
So,
Yes.
sir, now I'm getting the components as due to the the particles which are at a distance of a from that origin.
Hmm.
For that, I'm getting f into f of minus I minus j minus k, sir,
Hmm.
like the net. And then due to the diagonals, like this face diagonals, sir.
No, it's difficult to see in 3 dimensions. So of course, for every pair there is a different direction. So if you want to understand the direction, we have 3 edges, 3 face diagonal, and 1 body diagonal, right?
Yes, sir. Sir, I
The
forgot to take the unit vector of for the face
z,
diagonals, sir.
yeah,
That's why I
maybe.
got the mistake.
Yes. So you can see that, okay. Oh, you can try once again, not an issue. So what you
Yes.
can see that the edge will be like this, minus I minus j minus. So we can say f edge minus I minus j minus k. But if you look at the face diagonal, so let's take only one diagonal, not all. So if this is the diagonal, so this will have one plane, which is yz plane, yz plane. So it will have component minus j minus k, and same will be for all other three. So what we get is minus 2i minus 2j minus 2k.
Yes, sir.
Understood? And the last will be the body diagonal, and body diagonal will, just a moment. I mean, this is okay. This will be like root 2. This will be like root 2, no? So cos 45 will come. So
Sir,
this
we
will be
have
root
to
2.
take the unit vector of that.
Yeah. Unit vector of that. Yes. So yes. I mean, this is what we are doing. So the unit vector of this reaction will be upon root 2, right?
Yes, sir.
Sorry, this will be 2
Um,
root 2.
yes, sir.
Just a moment. Root 2 minus I minus j by root 2 minus root 2. No, this will be like by root 2 only. Yes. Because we have to add the vector unit vectors of 3 directions. So minus I minus j by root 2, then similarly 3 times. So this is the answer. Yeah.
Yes, sir.
So for body diagonal, the vector will be, you can draw a line like this. And this vector is easy to write. This vector is. So what is this vector?
Sir, minus I minus J minus K.
Correct. Minus I minus J minus K upon root 3.
Yes, sir.
So yeah, FH is fine, fine. So this is the answer. F net. Now
Yes, sir.
the value of FH will be how much?
Sir, it will be KQ square by A square. Sir.
F face diagonal.
Sir, it will be KQ square by 2A square.
And obviously the body diagonal will be
KQ square by 3A square.
3 square.
Yes, sir.
Yeah. So now it's only about you can substitute and simplify, you will get the right answer. Okay. So this is one way of solving in vector notation. And you can see the importance of vector notation. So in 3 dimension, this will be helpful. Okay.
Yes, sir.
Okay. So what we can do next is method 2. We can solve like this. So in any cube problem, this method is very powerful and it directly gives the answer without doing the vector calculation. So just think of any one charge, let's say this charge, and join the diagonal and join the base also. So you can see that what you are looking at right now is a right angle triangle, right? And if
Yes,
I
sir.
take this triangle outside of this cube, this is root 2a, this is a, and this is root 3a, right?
Yes, sir.
So always make this triangle. Let me change the color of it. So the blue line is representing the body diagonal, and the red one is the face diagonal, and this is edge. Okay. What else we need to realize that this is the line of symmetricity. This is the line of symmetricity. Okay.
Yes, sir.
Let's say this call this angle as alpha, this as beta. So every force must be resolved along the line of symmetricity. So you can see what is the angle between the edge and the line of symmetricity? Beta angle.
Yes, sir.
So any force acting along the edge will be beta angle away from the line of symmetricity. So we can say that the component of force along the line of symmetricity will be F edge cos beta. No matter how it is acting, doesn't matter. So this will be because we can understand it's going to be in same direction.
Yes, sir.
F edge cos beta, and because this will repeat 3 times, right? So this will
Yes.
add up all the edge forces all together. Now we are done with the edge forces. What is next? The face diagonal. You can see the face diagonal and the line of symmetricity makes alpha angle. So this must be a face diagonal cos alpha, but this will also repeat 3 times, right?
Yes.
And the one force which will not repeat is the body diagonal, because that's the only single force. Okay. And this is the net force answer, which is equals to 3. The edge will be kq square by a square. We know this. And cos beta will be how much? Cos beta is 1 by root 3.
1 by.
That's over. 3 kq square by 2a square, and cos alpha will be 2 by 3 under root. Okay?
Yes.
And the body diagonal is pretty much simple, kq square by 3a square, and we're done. So this is the final answer. Understood?
Yes, sir.
So every cube question we can convert into a triangle like this, and we just need to realize what is the angle between the line of symmetricity, which is going to be the body diagonal, with edge and the face diagonal. That's it. If I
Yes.
change, if I make the charge alternative, then one of the force will become negative because the direction will change. So let's say if okay, let me make it a separate diagram, not to confuse you. So if I make all charges alternative, you can see that the body will pull the edge will pull and the face will push, right?
Yes, sir.
Which means I have to take 2 as positive and 1 as negative. That's simple. So in the entire answer, we will take the edge cos, I mean, again, uh, cos beta will keep as usual. See previous page. So f net will be f h cos beta. Okay. And 3 times. And f body diagonal, but minus we have to make it 3f face diagonal cos alpha. So that's the only difference we have to make. Okay. So
Yes.
when charges are alternative in sign. Okay. So this is the question we need to know. So you can do one more problem here. Let's say if I give you a question like this, we have two equilateral triangles. We have two, not one. One is like this, and other one is these are two equilateral triangles of side length, let's say. Okay.
Yes, sir.
And now we have charges like this, plus, plus, plus on these three vertex, and uh, minus. The sides are parallel. So you can see the facing sides are parallel to each other. So that's a rule, and they have common center. So centroid of the first triangle is same as the centroid at the second, and these charges are, let's say, q, and at the center we have charge q naught. Find net force on q naught. That's it. So question is
Uh,
clear?
yes, sir.
Yeah. So go ahead.
So, so,
Oh, sorry. Yeah. Tell me.
sir, I'm getting the answer is 12q square by a square, sir.
12 q square, kq square, no? 12 kq square
Yes,
by
sir,
a
kq
square.
square.
I think this should be the right answer. So what we can see that all fours will add up, right? So the
Yes.
net answer is, I think, 4 f f f, yeah, 4f. So if I say the force due to anyone. This will repel like this. So if I call this force as F, then all, if you add all value, you will get.
Sir, I'm not able to hear you, sir.
Hello, hello.
Yes, sir, now I'm able to hear you.
Okay. Audible?
Yes, sir.
So the answer is 4F. If I choose F as the force between any two charge like Q and Q naught, so this will be KQ naught. Okay, it's not Q, it's Q naught upon the separation square, which is how much? So how much is the separation?
2 by 3 into root 3 by 2 a, sir. So
Yeah, so
it
it's
will be a by
A by
root
root 3. A by root 3. Very good. This is the right answer. But just make it KQ naught, right?
3. Yes, sir.
Okay, very good. So now we can do something more interesting. If we have any two charges, point-like charges, 2 point charges, let's say, and if both are positive, and if their magnitudes are Q1 and Q2, and the separation is G, the question generally which is being asked is like where we should put the third charge so that it remains at rest. So this is what you encountered in the last lecture while solving SC Verma.
Yes, sir.
So we have to put the third charge in such a way that it should remain at rest. So one thing is sure that we must keep the charge on this line joining the charges, right?
Yes, sir.
Now there is no question of putting the charge off this line. Like we cannot put somewhere here and expect equilibrium, or somewhere here expect equilibrium. That's not possible. So there are
Yes,
three
sir.
possible locations I can put. I can put in location 1, or region 1, region 2, and region 3. So we have three choices to put the charge, but we'll do it logically. So let's say the third charge is having some value. Let's call it Q naught, and we call it test charge. And we mentally understand the force. So Q1, Q2 both are positive, so both will repel, right?
Yes, sir.
And because both will repel, so there is no question of equilibrium. Similarly, the region 3 is also not a suitable choice. So these two, I mean, examples are like or conditions are eliminated. So we are left with only one choice. The third charge must be in between the charges Q1, Q2, that is region 2. Okay.
Yes, sir.
So now the question is where it should be. So you can think, okay, let's say it is going to be somewhere here. We don't know exactly where, but let's call it X. So this will be D minus X. And what we can do is, because it is in equilibrium, which means the net force must be
Sir,
0.
0.
So this is the problems based
Sir.
yeah. So let's call this as F1, this is F2, this is F1, because F1 will apply force right and F2 will apply force left. So balancing this force, we can get the answer, right?
Yes, sir.
And what we can get is Now what you can see that the balancing has nothing to do with the test charge, because it is going to be independent of the charge which you have taken. So any charge which you will bring will experience no force, and we'll learn later on that this is due to the concept of electric field. The point where the electric field is zero, any charge which you will bring there will experience nothing. So that's why the point of equilibrium depends on the Q1, Q2, not on the test charge at all. So as a rule, just remember as of now that point of equilibrium remains independent of test charge. So it is same. So d minus x upon x whole square is q2 by q1, and therefore you can write as under root of, okay,
Yes.
and we never square it, we always take the root actually. And you can see that if I for a while, if I call it r2, if I call it r1, so this is r2 by r1, right?
Yes.
And it is like a that r2 by r1 having the proportional relation with q2 by q1, right?
Yes.
Just okay. Yes. Okay. So R2 by R1 is Q2 by Q1. Okay. And this also helps us in understanding that the point of equilibrium divides the line into which ratio?
Sir.
R1 is to R2, and which is the square root of charge, right?
Yes.
So the point of equilibrium divides the line into the ratio of square root of ratio of charges. So R1 by R2 is basically under root of Q1 by under root of Q2. You can think this way also. So this will give you the internal division of the line joining the charges. Understood?
Yes, sir.
So this is one way of thinking, but let's solve for the x value. So d minus x is equals to root q2 by root q1 into x. So d we can write as x common 1 plus root q2 by root q1. X turns out to be, or you can say d upon, that's better way of writing, 1 plus. So the answer is very simple. Now what you need to realize that the answer depends on the ratio of charge, not the actual magnitude. Because when you take the ratio, the value will cancel out, only ratio will remain. So if I say this is, let's say, 4 microcoulomb, and if I say this is 9 microcoulomb, then what will matter is the 4 is to 9. Micro will not matter, 4 will not matter, 9 will not matter, because even if I make it 8 and 18, it's the same answer. Even if I make 12 and 27, same answer, right?
Yes, sir.
So what really matter for calculation is the ratio of charge. So even knowing the ratio is sufficient to get the point of equilibrium. We do not need the exact charge value. Understood?
Yes, sir.
And you can see x is from the q1. Okay, x is from the q1, so the answer is root q1 by q1 plus root q2. This is how to you can remember it. If x you take from the q2, then in the numerator q2 will come, and in the denominator the sum of the two will come. Okay.
Yes, sir.
Okay. So imagine the other scenario. Okay, now in the previous question, we were finding the point of equilibrium, assuming that this is fixed. This is fixed. Why? Because if you don't keep it fixed, then this will also experience force and it will move left and right.
Yes, sir.
So by fixing the the other two charges, we are only looking for the location of the test charge to achieve the equilibrium. Okay.
Yes, sir.
Now, if I change the sign of the two charge, so let's say this is again q1, this is again q2. Now, in which location, like if I divide again into back into the region 1, 2, 3, so now if I keep in the region 1, that's the test charge, and we'll keep the positive test charge just to make this as a tradition or convention. Now you can see if q naught is positive, what q1 will do? Will attract or repel?
So repel, sir.
Correct. So the f1 will be left. What about q2?
So attract.
Now to balance, because q2 is far away and it has to balance the force, then q2 must be bigger in value than q1, right?
Yes, sir.
So the q1 must be smaller, then only it is possible. If q1 is bigger, then this is not going to be possible, isn't it?
Yes, sir.
Because q1 is anyway close, so it must be small so that it can balance the force by the q2, which is bigger and farther. Now if I choose the point here, so this is also one possibility. But if I put some charge, if I put the charge somewhere in somewhere in between, q1 will push, q2 will also pull, so the equilibrium is not possible. And coming back to here, q2 will pull, q1 will push, so possibility is there, but for this to happen, q2 should be smaller than q1, right?
Yes, sir.
So if q2 is less than q1, this is possible, and if q1 is less than q2, this is possible. Understood?
Yes, sir.
So the whole idea is when charges are opposite, then the equilibrium will be beyond the line joining the charge, like not between, beyond the charge, either right or left. Okay.
Yes, sir.
And the way to remember is, we call it, the point of equilibrium will be near the poor. So near means close by, and poor means the weaker charge. So the point of equilibrium you will always find near the weaker charge, not the stronger charge. Understood?
Yes, sir.
So if, for example, if I give you the scenario like, if we have mm, plus 4 microcoulomb, let's say minus 9 microcoulomb, and if I ask you, where do you expect the equilibrium, left of, right of, in between?
So it will be on the left of the two of the system, sir.
So left of 4 microcoulomb, right?
Yes, sir.
That's correct. So you can call it X, and then you can solve the way you know. So you just balance the forces. This is D. So can you tell me what is X here? Just solve this question.
Okay, sir. Sir, I'm getting X to be 2D, sir.
Yeah, that's the right answer. Now, also what we need to realize that in case of opposite charge, the ratio of charge will be the external division, not the internal division. So let's say this is Q1 and we have Q2, and this is the D separation. So imagine, okay, let's take the case that let Q2 is less than Q1. So the point of equilibrium is going to be somewhere here.
Yes,
Correct?
sir. Sir.
Yeah, just a minute. So P is the point of equilibrium. Okay.
Yes, sir.
and therefore this will divide the, okay, so we can say the how to say this, the distance here is, let's call it r2, and this we can call r1, right?
Yes, sir.
So r1 by r2 will be the external division. Understood?
Yes, sir.
So you can directly find the answer with the division formula. So if you remember the division formula is mx1 plus nx2 by m plus n if it is for internal, and let's say you divide it into m is to n ratio, and x will be mx1 minus nx2. So do you know these formulas by any
Yes, sir.
chance? Okay. So what we can do is we can assume this as origin. You can choose left as origin, and if you can choose this as x-axis, you can get the answer directly. Okay. So what will get the answer? So for this case, uh, x equals to mx1. What is m? Root q1, right? So root q1 into x1 is 0 because it is at origin.
Yes, sir.
Mm, minus root q2 into d upon m minus n. q2. This should be positive value. mx2 minus nx1. Okay, I think we have just changed this mx2 minus nx1. So we take the inverse ratio. No? The ratio is inverse. So mx2 minus nx1, right? So this will just change
Yes,
the
sir.
value. So, or you can remember this way, like the ratio is r1, so r1 into q2. I mean, sorry, r1 into x2 minus r2 into x1, right? Like this we can write normally. This is like m is to n, right?
Yes, sir.
So r1 is how much?
So root q1, sir.
No, we don't need this. I think we can take the ratio x2 minus r2 by r1 into x1, and if you divide here 1 minus r2 by r1, x2 minus root q2 by q1 into x1, and x2 is how much? X2 is d. So d minus
Yes.
x1 is 0, so this is 0. So this is meaningful answer, d upon 1 minus. Okay, fine. And you can see that if q1 is less than q2, the sign will change. It means it will be on the left side instead of right side. Understood?
Yes, sir.
So the internal, we can also apply the internal division formula here, and let's say let's do it by the internal division. So okay, this is the external division. So you can just denote it the way you want. Plus and so let's take anyone as origin, and we know it is going to have the external division. So you can just choose some value here. Although the answer is on the left side, but what I'm choosing on the right side. Okay, intentionally. So what you can add the answer? So you can see this is a, let's say R2. So R1 by R2 is how much? 4 by 9 under root, which is 2 by 3.
Yes, sir.
So the XP will be how much? R1 Q2. Okay. So this is like Q1. This is Q2. R1 Q2 minus R2 Q1. Why we are doing this? Because it's a external division,
Yes, sir.
and it will lead to the same answer. So we can take again Q2 minus R2 by R1 Q1 minus R2 by R1. Let's substitute the value. What is Q2? Oh, value was 9. R2 by R1 is how much? 2 by 3. What is Q1? 4 upon 1 minus 2 by 3, right?
Yes, sir.
So this is how much?
Sir, I'm getting a bit confused while
Yeah.
replacing the values, sir.
Yes, just R1. Just so if we apply the external division formula, then mx2 minus nx1 by m minus n. So if I do so, mx2, okay. Something is wrong. I think we have misplaced or something. It is 4 minus 2. What? Okay, I have just made a mesh out of it. Just a minute. Okay. So what we are supposed to write is the x is defined as, okay, we solve in terms of coordinate now. So this is the first location. See, the ratio is this much, right? This is the ratio of the external division, isn't it?
Yes, sir.
So we write as R1 x2 minus R2 x1 upon R1 minus R2. We are writing the position, right? I mean, I just wrote the charge incidentally. So R1 is how much? Leave it R1. What is x1? Sorry, what is x2? D
Yes, sir.
minus. What is R2? R2. What is x1? 0 upon 1 minus 2. That's it. This is as good as writing D upon 1 minus 2 by 1.
Yes, sir.
And this is how much? 2 by 1 means
Mm,
D
3 by
upon 3 by 2, which is as good as minus 2D.
Yes, sir.
And this was your answer, right? If you remember, this was 2D. So I assumed towards the right side, but we got left when negative answer, which means the answer is on the left. 2D
Okay,
here.
sir.
Understood?
Yes, sir.
Okay. But of course, there's no need to solve this way. Like, of course, we'll do by the, it's good to balance and solve. That's easy. But if you can also understand this part, then it's really interesting. The division method. So let's solve some question on the internal division. So we have charge Q1, we have charge Q2. Let's say this is the R1, this is R2. And if both are positive, then we are going to get the equilibrium here somewhere. So let's say this is origin, and this is the x-axis. You can choose anyone as origin, so that's easy. So this is 0, 0, and this is x-axis. So what you can write is so if the D is a separation, so the coordinate of the Q2 will be D, 0, right?
Yes.
So what we are supposed to write is x1, the R1, which is the ratio, we are taking the ratio R1 x2 plus R2 x1. Why we have? Because it's internal division upon sum of the, there's a formula. And now this is done. So R1 x2, R2 x1 is 0. This is as good as writing 1 plus, and we know the answer. R1 by R2 is under root Q1 by Q2. So this is
Yes.
same as, you can see this is in fact easy if you practice a bit. Like after a while, this is easy because we are not doing any calculation of writing the force, taking the root and solving it. We can do it almost mentally after some practice. Is this clear?
Yes, sir.
Yeah. So the internal division and external division, we can take care by this method. Okay.
Okay, sir.
Okay, so I have actually another lecture, I mean, right now. So I'll continue the problem solving in the next lecture as well.
Okay, sir.
So next lecture, we may keep on Sunday morning if possible. You just let me know.
Sir, tomorrow's lecture, sir.
Tomorrow, actually, yeah, maybe possible. I mean, hopefully, yeah, tomorrow also, not an issue.
Okay, sir.
Tomorrow, same time, 8 o'clock. Okay?
Yes, sir. Thank you, sir. Bye, sir.